Hello students, in the last session we had discussed about diffusion, what is diffusion, types of diffusion and diffusion mechanism, and the last topic what we discussed is what are the factors that affect diffusion process. Continuing with that, in today's session I will be covering fixed laws of diffusion. So we got two laws, fixed first law of diffusion and fixed second law of diffusion. Now here this diffusion of these atoms from one point to other point, it depends upon the concentration gradient. So depends upon the concentration gradient. So based on this concentration gradient, so a scientist by name FICK'S has conducted a study and he has given two laws. He has given two laws that is called as fixed laws of diffusion or laws of diffusion. Fixed first law of diffusion and fixed second law of diffusion. So we will discuss the statement of this first law and second law of diffusion. So coming to the first one, fixed first law. The statement says that the flux of atoms moving across a unit surface area in unit time is proportional to the concentration gradient under steady state condition. So here the two laws given is, one is for steady state condition and other one is for non-steady state condition. What is steady state condition? What is non-steady state condition? Steady state condition is one where the concentration of atoms or concentration of movement of atoms will proportional to the time, whereas unsteady state condition is one where the concentration of atoms or movement of atoms will be not proportional to time. So that is once again first law says for steady state condition, second law for that is unsteady state condition. Statement says that flux of atoms. So flux of atoms, that is nothing but amount of atoms that is getting diffused. That is given by the letter J. Flux of atoms moving across a unit surface area. A unit surface area is taken. So unit surface area in unit time. So unit time, unit surface area, the amount of atoms that is moving is proportional to the concentration gradient under steady state condition. That is what the statement says that. So flux of atoms, that is the quantity or movement of atoms moving across a unit surface area. You take it a unit surface area and unit time is proportional to the concentration gradient. So that is what unsteady state condition. So finally the statement, according to statement, so it is represented as J is equal to D into dC by dx. Now this concentration gradient, so it can be, it is nothing but amount of atoms that is moving in through unit cross section area and unit time. A graph can be plotted taking the distance along x-axis and volume of concentration on y-axis. X-axis is distance, so volume of concentration of atoms in is y-axis. Now if we take a metal, so if we take this is as a material through which atoms are getting diffused. So this is one surface, this other surface. So as it moves across this, so this is the distance x, this is the distance x. So the time taken, the atoms start diffusing from this end and it comes out this. So that is the amount of diffusion of atoms. So this is the distance x. So that is represented on x-axis. Concentration, the amount of atoms moving on y-axis. Now here the final equation according to the first law is J is equal to D capital D into dC by dx. So dC by dx is the concentration. Initially, so when atom starts diffusing it at this end, so initially it starts after a certain time interval of time and it passes through a certain distance x. So concentration at this point will be C, and when comes out concentration will be, this is C1 and C2. Concentration at this point is C1 and when comes out it is C2. Now we can plot a graph. So with respect to time, that is after every certain interval of time, what is the amount of atoms that is getting diffused. It starts from this end, it should come out this through this end. So with this covering through this distance x, what is the amount of atoms that is diffusing at different interval of time. So if you study that, you can plot a graph, that is concentration at C1 is here. So if you plot, put it down, so it will be at a distance x1 and similarly concentration will be at C2 will be x2. So This flux of atoms that is moving across is represented by this concentration gradient. So hence we can arrive at the final equation as J is equal to capital D into dC by dx. So where capital D is the diffusivity rate, at what rate the atoms are getting moved or getting diffused. Capital D is diffusing rate. D, small d Cx, small d dC by dx is nothing but concentration gradient. So what is the concentration at this point C1? What is the concentration at this point C2 after it moves at a distance of x? This is the distance, that is thickness of the material. So C is the volume concentration of atoms, J is the number of atoms per unit time per unit area. That's what the definition says. Unit cross section area and unit time and unit area. X is the distance that is between the planes. This is the distance. It is nothing but the thickness of the material. So from this end to this end, this is the material. If you take the amount of atoms getting diffused, this distance x, x is the distance x. So here the equation finally it will be given as J is equal to minus D into dC by dx. Minus negative sign is there. Negative sign because flux moves from a higher concentration to lower concentration. So concentration where when the concentration is higher, from there it moves down to concentration where it is lower. Hence we use a negative sign. So J is equal to minus capital D into dC by x. C is the concentration. So concentration changes with respect to distance. So that is, we can represent it further as minus D into C1 minus C2. C1 is the concentration at this point, that is at this end, and C2 is the concentration at this other end. So C1 minus C2. This is the distance x1, this is distance x2. So x is nothing minus D into C1 minus C2, concentration at point 1, concentration at point 2. x2 is the distance. So this is the distance here and distance here. So finally, according to the statement, so equation is J is equal to minus D into dC by dx. So this is the law given for the steady state condition. Hence it can be also called as Fick's first law of diffusion or Fick's steady state condition law. Coming to the second law, the other law is, so Fick's second law of diffusion, it says that or unsteady state condition. So unsteady state condition where concentration varies with time or distance. It is not proportional to the time, proportional to the distance. Here it is a proportional, hence we are getting a slope, a straight line. So if it is not, so practically speaking, it will be not. So in most of the cases where, suppose if we take an example where carbon is induced to iron. So this iron piece where carbon is induced. So there the concentration varies with respect to time or distance. So that is what unsteady state condition. So what the law says for unsteady state condition. So come to the statement here, it says that rate of constitutional change is equal to the diffusivity times rate of change of concentration gradient in unsteady state condition where it is varies with respect to time. So if you take a graph once again, x-axis that is distance, y-axis concentration, you can see here you are getting a curve, here you are getting a curve, here you are getting a straight line, that is proportional, here it is not proportional. So this is the distance at x1, concentration is C1, at x2, concentration is C2. In between at any interval of time, it is not proportional, that is amount of concentration will be not proportional to the distance, it varies, it varies. That is what it says that unsteady state condition. So here, that's what it is shown here, dC by dt is not equal to 0. T is the time interval. So finally, the equation for this second law is nothing but dC by dt, that is concentration with respect to time, will be equal to capital D into d squared C divided by dx squared. Since it varies with respect to time, so the equation will be capital D into d squared C divided by dx squared. So where concentration and that is distance varies with respect to time. So this is Fick's laws of diffusion, that is first law of diffusion and second law of diffusion. One is for steady state condition and other is unsteady state condition. So students, in this particular model, till now we started with crystal structure. What is crystal structure? Then imperfection. So what are the different type of defects? Imperfection, nothing but what are defects that are seen. So then diffusion, so movement of atoms, then diffusion mechanism, then laws of diffusion, factors affecting diffusion. This is the first part of this model. The second part is studying the mechanical behavior of a material. Now what is mechanical behavior? So the behavior of a metal under different loading conditions. How the metal behaves under different loading conditions. So that is called as mechanical behavior. Now what is the necessity of studying this mechanical behavior? Now different materials will have different properties. Different materials will have different properties. So as a user, you will be having your own requirement, so certain properties. Now if I want to choose a material, I should know what are the properties that particular material has got. What are the properties that material has got? Based on that, I can select that required material. Hence, it is very much necessary to know the mechanical behavior. Mechanical behavior defines the properties of the material, how the material behaves under different loading conditions. Now here different type of tests can be conducted to study the mechanical behavior. Among them, tensile test is the most important, most widely used type of test conducted, because we can study a lot number of properties if you conduct a tension test. So in this session, I will be covering a stress strain diagram. So when we conduct a tension test, so after or during the process of the tension test, so we observe the values and plot a graph that is called as stress strain curve. So a plot or graph plotted taking stress and strain. Then the next topic I will be discussing is elastic properties. So what is elastic region? So what is plastic region? What are the properties we can study in the elastic region? So there once again we can have two subdivisions. So properties, that is elastic properties in the linear region and elastic properties in the non-linear region. So these are the things I will be covering in this session. So coming to the first thing. So as I told, tension test is conducted. How tension test is conducted? Take a specimen. So specimen will be fixed on a UTM, that is universal testing machine, and gradual loading is done. So as we go on increasing the load, after certain interval of time, the specimen starts elongating. Elongation is nothing but where it changes its length. So as length changes, its diameter decreases. So as you go on loading on both ends, so after certain interval of time, the elongation starts. So we continue loading. And for every interval of time, we note down the stress and strain values. Stress is the load what we are applying. Strain is the elongation. Strain is nothing but elongation. Both the values are noted down. So we continue loading, and note down the values. At a particular interval of time, specimen breaks. At a particular interval of time, so when maximum elongation takes place, specimen breaks. So based on the values noted down, a plot will be done or graph will be plotted taking the stress values. Stress is nothing but the load, stress and strain values. So this can be done for both a ductile material. Test can be conducted for both a ductile material and for a brittle material. Correspondingly, a plot can be plotted for a ductile material and for a brittle material. The purpose of drawing this plot is we can study different properties by analyzing the graph. By analyzing the graph, we can study the different properties. So what are those properties? So this is the this stress strain curve for an material cast iron, that is brittle material. In materials, we can have two types of material, that is ductile material and a brittle material. So ductile material where we can see the elongation with the apply of load. Brittle material is one where specimen suddenly breaks when we apply the load. Example, if you take glass, if you take an iron piece and a glass, if you drop from the same height, so glass breaks where iron does not, or cast iron, mild steel does not break, because mild steel is your material, that is glass is a brittle material, so this is a ductile material. So that is the difference between ductile and material. So the graph changes for a ductile material and a brittle material. So this is the graph, that is stress. This x-axis is the strain elongation, y-axis is the stress. So this is the graph how we get for a cast iron material, that is a brittle material. Similarly, this is the stress strain curve for a mild steel, that is ductile material. So here when you plot a graph, you can see that as the elongation increases, so as the stress value increases, elongation also increases. So this is for a cast iron is nothing but a brittle material. So that is point should be remembered. So here you can see that graph starts from here, it moves like this, and finally it reaches a point where specimen breaks. So here we can divide this curve into two regions, that is elastic region and plastic region. So what is elastic region and what is plastic region? Now elastic region is one where when you apply the load, specimen gets elongated. Once we release the load, specimen goes back or comes back to its original position. Example, if you take a rubber band, if you pull it, so it gets elongated until you apply the load. So once you release the load, it comes to original position. That is called elastic region. That is called as elastic region. Then plastic region, second one. Plastic region is one where, so you apply a load, so then even after you release the load, specimen does not come back to your original position. So whatever elongation that had taken place, so that will be there even after releasing the load. That is called as plastic region. So elastic region, we can have two regions. One is elastic region and other one is plastic region. So this is for a cast iron, it is for a brittle material, how will be the stress strain curve. Similarly, here this is one more curve, that is for a it is your ductile material. So in case of brittle material, as I just now mentioned, if you drop, the glass suddenly breaks, so we cannot study the intermediate ranges. So it starts, it begins and finally it breaks. We cannot identify the clear differentiation between elastic region and plastic region. So where elastic region ends and where plastic region starts, because this breakage will be sudden breakage. So hence we cannot identify clearly, hence we cannot study more properties in case of brittle material. But on the other hand, if we take ductile material, so the changes will be gradual changes. Changes will be gradual. Hence, we can study the properties at every interval of time where changes takes place. At every interval of time where changes take place. So this is for a mild steel. So mild steel is a ductile material. Mild steel is a ductile material. Once again, you can plot a graph after conducting a tension test, taking elongation on x-axis. That is sigma I is nothing but stress on y-axis. So here, if you observe the curve, so it starts from this point, so where stress and strain will be 0. You go on loading, elongation starts. So it reaches a point here. So this point is called as proportional limit. So further we have got one more point, this is called as elastic limit, and this is called as upper yield point, lower yield point. This is ultimate strength and this is the failure point. So these are all things we can observe when we plot a graph. So here initially for a stress and strain 0, it starts from this point. So then it reaches this point. Up to this point you get almost a straight line. That indicates that stress will be directly proportional to strain. So whatever amount of loading is done, same amount of elongation will take place. So up to this region it will be a straight line. So this limit is called as proportional limit. So what is proportional limit? Proportional limit is the limit up to which the stress will be proportional to strain and it obeys Hooke's law. Hooke's law states that stress is proportional to strain. So up to this point, proportion, that is called as limit, proportion. So it will proportion, whatever amount increase in stress, same amount will be increase in the deformation, that is nothing but strain. So that limit is called as proportional limit. It is a limit up to which the stress is proportional to the strain and it obeys the Hooke's law. Then further if we continue, so this is called as elastic limit. So elastic limit, so where after crossing the proportional limit, crossing the proportional limit, so deformation will be faster. We can see that here it is straight line, then it starts, straight line starts taking a curvature. So elastic limit, as I just now mentioned, elastic limit is one up to which whatever load you apply, so once you release the load, it retains or it regains its original position. That is elastic limit. So then further move to this point is called yielding point. So yielding point is one where deformation actually starts. That is, for very small change in load, so deformation will be very large. So yielding, specimen starts yielding. So here we can observe two yield points, upper yield point and lower yield point. So this point is called as upper yield point. So upper yield point is one where actual deformation starts. So deformation starts. So that is called as upper yield point. So you can see that after this the curve drops down. So the stress value, even though if you increase, stress value decreases with increase in elongation. Elongation will be more faster after crossing the upper limit. So then it reaches a point, see you can drop in the curve, and once again the curve rises. So this point is called as lower yield point. So lower yield point is one where deformation will be maximum. So deformation will be maximum. So that is lower yield point. So once again, so there will be rise in the curve and it reaches a point. This is called ultimate strength. So further you continue loading. When you continue loading, so at a particular point, so you get this is the maximum position of the curve. So ultimate, so the loading will be ultimate strength, that is the maximum load the specimen can take. So that is ultimate strength, that is called as ultimate strength. Now further you can see that once again curve drops down, further drops down. So after it reaches a maximum position, curve drops. So even though if you start loading, so maximum load it has taken, it will not take further load. So further at a particular point it breaks or it fails, that is called as failure point or failure strength. So one point you have to remember is that ultimate strength will be always more than the failure strength. So once it reaches ultimate strength, so then drop in the curve, so finally at a particular point specimen breaks. So that point is called as failure point, strength at this point is called as failure strength. Ultimate strength will be more than the failure strength. So these are the properties you can study in that is ductile material. So we have taken mild steel as an example. Similarly, brittle material, we cannot observe these changes, you can compare both the curves. So once again it rises, it will be almost straight line. So then between this region and this region, so the process will be very fast that you cannot observe any changes. Changes takes place drastically. Changes takes place drastically and specimen suddenly breaks. We cannot observe all these changes. Hence, so it is very much important to study the changes in case of a ductile material. So that is about the elastic, ductile material and brittle material. So stress strain curve or stress strain diagram we call that. So in the brittle material and in the ductile material. Next, elastic properties. So we just now observed that what is the elastic region and what is the plastic region. So what are the properties we can study in the elastic region and what are the properties we can study in the plastic region. So if you observe this mild steel also, this is the elastic region, this is the plastic region. So in the elastic region, what are the properties we can study and what are the properties we can study in the plastic region. So elastic properties, the properties what we study in the elastic region or the properties what are observed in the elastic region is called as elastic properties. Similarly, what are the properties that are observed in the plastic region are called as plastic properties. So here under elastic properties we can further classify it into two types. One is linear, other one is non-linear. So linear is one where the curve will be almost straight line up to this point. Up to this point it will be straight line and then it suddenly takes a curvature. That is called the linear region. So linear region is one where stress will be directly proportional to strain. Non-linear is one, so he can from this up to this point it is linear, then you can see a small curvature, that is non-linear, where it will be not proportional, stress will be not proportional to strain. So what are the linear properties we can study, what are the non-linear properties we can study. So coming to the first one, linear properties. So linear elastic properties. So here we can study four different properties. So first one stiffness, second one elastic strength, then resilience and modulus of resilience. So 4 properties we can study in the linear region, in the elastic region itself, linear elastic region. That's what's called as linear elastic properties. So first one is stiffness. So what is the definition of stiffness? It says that a resistance offered by a material to elastic deformation. Resistance offered by the material for elastic deformation. So what do I mean by this? So if you take this as a specimen, if you start loading, so specimen offers resistance. It offers resistance. So when your load is more than the resistance offered, then only we can see the deformation. So that is what it says, that resistance offered by material to elastic deformation. So if you take a rubber band and if you pull it that, so if when your load is higher, then only the changes can take place. So if you pull it, you can experience that. So material will not easily accept that. Material will not easily accept that. It offers resistance. It offers resistance. Any material if you take, it offers resistance. That is called as stiffness. That is called stiffness. The resistance offered by the material against plastic, that is elastic deformation. One more term what we use for stiffness is Young's modulus. Young's modulus. So your stiffness is also called as, that is Young's modulus. That is the first property, linear elastic property. Second one is elastic strength. So it says that it corresponds to the highest stress at which behavior of a material remains elastic. So maximum point where it crosses the elastic region and enters the plastic region. The strength at that particular point, if you take at this point, so this point where what is the strength at this point is called as elastic strength. Similarly, what is this, the elastic limit? What is the strength at this point? So at this point, what is the strength the material has got? That is called as elastic strength. It says that it corresponds to the highest stress, maximum stress in the elastic region. You should remember that maximum stress in the elastic region at which behavior of material remains elastic. After that, it enters the plastic region. That is the second property we can study. Then third one is resilience. So it says that it is the ability of a material to absorb energy when it is loaded elastically and gives back the same energy once load is removed. Resilience, ability of a material to absorb energy when it is loaded elastically. So if you take once again rubber band, if you start pulling it, it absorbs energy. As you apply load, it goes on absorbing energy. That's why it says the ability of material to absorb energy. When you are loading it elastically, it starts absorbing energy. So that is when it's loaded elastically. Once you release that, it load is also released. Once the load is released, it the energy that was absorbed, it releases that energy. That is called as resilience. Ability of a material to absorb energy when it is loaded elastically and gives back the same energy. Once you release the load, rubber band comes to original position. Whatever energy that was absorbed by the material, that energy is released. So that is called as resilience. Third property, third linear property. Then fourth one is modulus of resilience. It says that the strain energy stored by the material per unit volume at elastic limit is known as modulus of resilience. Now, if you take this curve, so resilience is one. What is the maximum amount of energy that is absorbed in the elastic region? Now, I don't want maximum point. I want what is the energy absorbed at this some intermediate point. If I want to get the what is the energy that is what is the ability of absorbed energy, an intermediate point. So that is called as modulus of resilience. It says that strain energy stored by the material. What is strain energy stored is nothing but what is the amount of energy that is absorbed per unit volume at elastic limit. So at any volume, but it should be within elastic limit is known as modulus of resilience. That is given by sigma s squared divided by 2E, where E is the Young's modulus, what you get here. Young's modulus, 2 is the, it is 2 into E, that is Young's modulus. So if you want to find out what is the absorbed energy at any intermediate point, suppose at this point, So what is that energy absorbed? That is given by modulus of resilience. So these are the properties, that is what we study in the linear region.